Good morning. Today we're going to be talking about how to design high-pass filters. We've been talking about how to design low-pass filters, but we don't know how to do that. What would happen if we want a high-pass filter? Well, it turns out to be relatively simple if we notice the following thing. H of z, right, the z transform of h of n, is written like this, which has a Fourier transform equal to this, right? We substitute z for h of e to the j omega. Now, what if we substitute z for minus z? Now we would substitute e to the j omega with minus e to the j omega. Now this negative that we have here, we know that -1 is equal to e to the j pi, right? Using Euler's equation, this term here is going to be equal to -1. Now, here we have two exponential functions multiplied together, which will give us this term here. Or if we look at that more closely, put the minus n inside, this looks very much like the original transform, Fourier transform we had, except that instead of having omega, we have omega minus pi. And so it's the same function, simply shifted by pi. Now, in the discrete universe, we know that the low frequencies are close to 0. The high frequencies are close to pi. So if we shift everything by pi, what used to be the low frequencies become the high frequencies, and so forth. So in other words, if we had a magnitude function that looked like this, high close to 0, low close to pi, which would be something like a low-pass filter. If we shift this by pi, it would look like this. Now, usually in our filters, we're only looking from 0 to pi. Here I wrote the whole thing because we need to be shifting it and see what it looks like. So if we shift this by pi, this at 0 becomes pi. What was at minus pi becomes 0. And so this thing here, if we only look between 0 and pi, at the low frequencies it's attenuating, at the high frequencies it's passing, so this is a high-pass filter. So in other words, if we take a low-pass filter and shift it by pi, it becomes a high-pass filter. And that's what we're going to do to design our high-pass filters. In other words, if we have an h of z that satisfies these specifications, and again, we usually talk about this, or we look at the specifications between 0 and pi. Here I'm just stretching this out. I'm looking at more frequencies, so when we shift it, we know what's happening. So this is a low-pass filter, right? Passes frequencies close to 0, attenuates frequencies close to pi. Now, if we shift this by pi, this is what we get. We get a frequency that attenuates the low frequencies and passes the high frequencies. So if h of z satisfies these specifications, h of minus z is going to satisfy these specifications. And so that's what we're going to do. We're going to design a low-pass filter and then substitute z for minus z and convert it into a high-pass filter. For example, let's say we wanted a high-pass filter for these specifications. We need to take these specifications and convert them into the low-pass filter specifications we're going to use to design our filter. Now, if we take these specifications and repeat them as we know it's going to do because it's a discrete system, and then shift it by pi, what we're going to get is this down here. Pi is going to turn into 0, 0.9 would be 0.1, and 0.8 will be 0.2. And so this is, we would design a filter for these low-pass specifications, and then when we substitute z for minus z, we'd get a filter for these specifications up here. Let's go through a complete example. Okay, so let's say we want a system that has a analog to digital converter, a digital to analog converter, and a digital filter. And we want this whole system to meet these specifications. First thing we do, as always, we convert the specifications from omega to, or from continuous time to discrete time, from big omega to little omega. And this is the frequency used because we're using sampling here. And so we go from this to these specifications, right? We find the specifications for h of z. 200 pi, 400 pi become 0.2 and 0.4 because the sampling frequency is 1000 hertz. So we want to filter for these specifications. We need to convert it to low-pass filter specifications. So that's the first thing we do. 0.4 pi becomes 0.6 pi, 0.2 pi becomes 0.4 pi, and 0 becomes pi. Right, we shift all of these by pi. Now, once we get it into this form, the procedure is exactly like the low-pass filters we've been designing. I'm going to go through it just to see another example, but there's nothing new here. So the first thing we do, of course, is we pre-warp to get the specifications for HA of S for the analog filter we're going to design. Let's say we select t equal to 2, so we get these equations. And we convert from these frequencies, 0.6 pi and 0.8 pi, to these frequencies here, 1.3 and 3.1 radians per second. These specifications are in dB, so we convert it to non-dB as we've been doing before. And then once we have it in non-dB, we can get K epsilon squared in A. K by inspection is 1. We use this equation to solve for epsilon squared. We use this equation to solve for A, and then we have all our unknowns. Once we have K epsilon squared in A, we can get N. We use the same equation to get N. This time the equation gives us 2.45, so we can use any order filter greater than or equal to 3, so we choose equal to 3. Next we can get omega C. This is the equation for the inequalities for omega C. Omega C, then we see it has to be basically between 1.5 and 1.7, so I'm going to choose 1.6. And once we have omega C and N, all that's left is getting the poles. We can get our transfer function. These are the 3 poles we want. Again, we know that the poles are equally spaced around the unit circle, symmetric with respect to the real or to the imaginary axis. So these are our 3 poles. 360 degrees divided by 6, right? So this is going to be 2 pi divided by 1, 2, 3, 4, 5, 6. So each of these is going to be 2 pi divided by 6, which is pi over 3. So pi over 3, 2 pi over 3 would be this angle, 3 pi over 3, and 4 pi over 3 for the 3 angles. By inspection, we can see that P1 is at -1. Once we get P0, P1, and P2, we can multiply for the denominator. Of course, this is assuming that omega C is equal to 1. We multiply this out, make sure, verify that this is what you get. And once we get the denominator, we can get HA of S substituting again for omega C, putting omega C back in the equation. So this is our final transfer function once we substitute omega C equal to 1.6. And so this is our analog filter that we design. So we take our analog filter, we convert it to the digital filter, again using the bilinear transform. Since T is, we substituted equal to 2, it simplifies this a little bit. We just substitute S for z minus 1 over z plus 1 in the equation up above, and we have this equation here. This is a few multiplications and nothing extraordinary. We multiply everything by z plus 1 cubed just to get rid of the denominators here. So this is our equation, and then this is just substituting out. Make sure I didn't make a mistake adding all of these terms together. Once we multiply it out, add the terms together, this is what I got. Of course, we want to normalize this. We want the highest power to have a coefficient equal to 1. So we're going to divide by 13.496 and get this equation down here. And so this is our low-pass filter that will meet the specifications. So we need to take this and change it into a high-pass filter. As we said before, we just changed from z to minus z. And so we substitute all the z's here for minus z. We see that if it's in even power of z, it stays the same, right? Minus z squared is just z squared. Minus z to the cube is minus z cubed. And minus z, of course, just becomes minus z. And so this is the equation that we get. Again, normalizing, we want the highest power of z to have coefficient equal to 1, so we divide by minus 1 to get this. And this is our final answer. This would be the h of z that gives us the high-pass filter. I want you to do a couple of these problems. So in other words, basically repeat the problem for these two cases, for these two specifications. Again, the sampling frequency is equal to 1,000, and the magnitudes are 1, minus 1, and minus 5. The only difference is here it's 200 pi and 300 pi, and here it's 200 pi and 230 pi. So go through this, design a couple of filters.